Hello, my name is Parth, and this is my magnetic molasses lab video for Lab 6 in Physics 2212. So the purpose of this lab, in this lab, I will explore Faraday's law by observing the interaction between a bar magnet falling through a conductive tube of aluminum foil. Additionally, I will develop a computational model of the system to compare my theoretical predictions with my collected observational data, and some assumptions to keep into consideration. The computational model simplifies the physical bar magnet by treating it as a single point dipole rather than a solid object with volume. The conductive aluminum tube is modeled mathematically as a stack of individual non-interacting conductive rings rather than a continuous cylinder. When using Newton's third law to calculate the force exerted on a falling magnet, you must assume that the tube itself remains fixed in place. So the glow script model simulates the experiment by approximating the bar magnet as a point dipole and the conductive tube as a vertical stack of non-interacting rings. I will modify the code to calculate the changing magnetic flux and induced current in these rings to determine the magnetic force on the falling magnet and iteratively update its motion. So preview of the main result, the experiment time was 1.50 seconds and the computational time yielded 1.48 seconds for the magnet to fall. The Faraday's law is it explains how the current is generated as the bar magnet falls through the tube. The magnetic flux passing through the conductive aluminum foil changes over time. The Lenz's law explains the direction of the force, and the current induced by Faraday's law produces its own magnetic field, which interacts with the falling magnet. And on the left, this is what Lenz's law looks like, and on the right is what creates the current with the changing flux. All right, so this is our setup. Firstly, we're going to define the system, which is the bar magnet, and the surroundings, which is the aluminum tube and the earth. So the setup is we mark the north pole of the bar magnet using a magnetometer app from the previous lab experiment. Then we hold the aluminum tube vertically with one hand and position the magnet just above the top opening. Then we align the smartphone camera to capture the tube's entire length. Then we ensure any supports used to hold the tubes are non-ferrous. Record a video while dropping the magnet through the tube, and then we find the video timestamps for the magnet's entry and exit. Then we calculate the fall duration by subtracting the entry time from the exit time. And then we average this 5 separate trials, and we get to see the average time. Okay, so our experimental conditions. So the aluminum foil's length was 47 centimeters. The free fall outside the foil was 0.94 seconds, and the free fall inside the foil was 1.48 seconds. And this is just a demonstration of us performing the experiment. All right, so this is my GlowScript code. This slide and the next slide is my GlowScript code, and I'll just give a concise understanding of what I wrote. So in this GlowScript code, I first initialize physical constants and model the aluminum tube as a stack of conductive rings and the magnet as a point dipole. Inside the main simulation loop, I calculate the changing magnetic flux for each ring to determine the induced current and the resulting upward magnetic force on the falling magnet. So this is also a continuation of my GlowScript code, and this is what the GlowScript code looks like, and it's quite cool to understand that the velocity graph looks like a dome. All right, so some possible sources of error. Measurement precision, so small inaccuracies in the measuring of the tube's geometry, like its radius or thickness, or determining the exact start or stop times from the video can significantly alter the calculated resistance and observed results. Then we can think about the magnetic moment uncertainty. So the computational model relies entirely on the magnetic moment value calculated in Lab 3. So any errors from the smartphone magnetometer app will directly cause the simulation to calculate incorrect forces. And then the model simplification. So the code simplifies the physical reality by treating the bar magnet as a single point dipole and the continuous aluminum tube as a stack of non-interacting rings. And lastly, so what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So the magnet would fall extremely slowly, potentially appearing as floating or stop moving entirely inside the tube. So the cause of this is Ohm's law, and as resistance approaches zero, the induced current becomes nearly infinity. And so the result is that this massive current generates a magnetic force strong enough to almost perfectly counteract gravity. And what if the holes or slots were cut into tubes? How would this affect the rings currents in your model? So the disrupted currents, so cutting slots breaks the closed circular loops required for the eddy currents to flow effectively, drastically increasing the resistance. Then the reduced force, according to Ohm's law, this increased resistance caused the induced current to drop significantly, weakening the magnetic braking force, and then a faster fall with the opposing magnetic force largely eliminated. The magnet falls much faster, approaching the speed of free fall.